Hello everyone, this is STAT 100. I am now doing section 8.8, the completion of chapter 8. This is choosing the sample size. We have skipped, as I mentioned, skipped sections 8.6 and 8.7, which are not in the course. So we went directly from 8.5 now to 8.8. So choosing the sample size is about experimental design. And this is part of statistics. Sometimes data is just given to you. Somebody else has gathered the data, somebody else has designed the experiment. You may have to analyze the data, but more often you will have to design the experiment and then collect the data and then report on the data. So you'll have to do all of those phases of an experiment. And the issue of experimental design is a very important one. We want to design experiments so that they give us the information that we want at a minimum cost. If we, say, had a very small sample, we would have a lot of uncertainty, a very wide confidence interval, and that would maybe not give us the information that we wanted, so that experiment would have been done for no good reason. We would have simply wasted the money. On the other hand, if we go overboard and design an experiment that is too elaborate, that has a sample size which is too large, then we also are spending money that we didn't have to in order to obtain a result. So this aspect of experimental design is about finding the sweet spot in the sample size. So we want to find the sample size which is adequate but is not too large. So let's take a look at an example, and this one is from the textbook. So we want to estimate the average daily yield of a chemical process. So this is kind of an engineering example, and since it's a measurement that we're taking, mu is the quantity of interest to us, and we want the margin of error in our confidence interval for mu. We want our margin of error to be less than 4 tons. So we have to accept a certain amount of uncertainty in our answer, but we want to limit that uncertainty to 4 tons in either direction. And we want to be 95% confident of our results. So this is well on the way toward having enough information. So let's see what this tells us about the sample size. We want the margin of error to be less than 4 tons, and we're 95% confident. That means that the margin of error is 1.96 times the standard error. That's with a 95% confidence gives us this number 1.96. Okay, so what we want is 1.96 times SE is less than 4. And that's from this first equation. That's a condition. The margin of error is less than 4 in this problem. That's what we want the margin of error to be less than 4. In other words, the width of our confidence interval is 4 in either direction. 8 actually is the width of our confidence interval. So that condition translates now into this condition on the standard error. Now we substitute our formula for standard error. We know that standard error is, let me use sigma in this case, sigma over the square root of n. Okay, so combining those previous two tells us that 1.96 times sigma over the square root of n has to be less than 4. All right, so we can do a little bit of algebra on this guy. We've got 1.96 sigma is less than 4 times the square root of n. I just multiplied this square root of n over. Now I'm going to divide by 4. 1.96 divided times sigma divided by 4 has to be less than the square root of n. And so I now square both sides of this equation. 1.96 squared, sigma squared, over 4 squared has to be less than n. So this is a condition on n. It tells us that n has to be bigger than a certain number in order to satisfy our condition. And remember, our condition was simply this, that the margin of error is less than 4 tons. That was what we started with. The logical implication of that is that we have this condition on n. So n has to be bigger than some number. Now, the problem with this expression is that there's still an unknown. We don't know sigma. Sigma is the population mean for the population, but as usual, sigma is not available to us, just like mu is not available to us. And if we knew mu, we wouldn't have any problem at all. And if we knew sigma, we can figure out n exactly, but we don't know sigma. So this leaves us in a bit of a bind. Now, what we have done in the past for sigma is to make this approximation. Sigma is approximately s, where s is the sample mean. We can't do that in this case because we haven't done the experiment yet. We don't know s because we haven't done the experiment yet. Right? We're designing the experiment, so we haven't done it yet. So we can't use our usual method for approximating sigma. We have still a few possibilities, a few options, though. We'll have to be a little bit creative. One way to approximate sigma is to use s from a previous experiment. And so that is about the best we can do in this situation. So there's no magic fix for this. We can use we can approximate sigma by an s from a previous experiment, a similar experiment. And there's one other thing that we can do, and that is that, remember that sigma is approximately the range divided by 4, and this number 4 can change depending on the size of the population. So that is another kind of really rough way to approximate sigma. So take the range of all previous measurements that we've ever seen. They will have some kind of range. So here's all the measurements that we've ever made. And what we're doing essentially is saying, well, all those measurements are within about 2 standard deviations of the mean. We're going to cross our fingers and hope that that's true. And so that this range here, the difference between the largest measurement and the smallest measurement, should in that case be about 4 standard deviations, because we're assuming that measurements are within 2 standard deviations of the mean. So that's where this formula comes from. We had a bit of a discussion about this, I believe, in chapter 2, early on in the course anyway. This is a little more elaborate discussion, but the end result is the same. That this is, in many cases, a reasonable approximation to sigma, the standard deviation for the population is approximately the range of all measurements we've observed divided by 4. So you have to have something in order to do this. You need to have some measurements available, some either previous experiment in which you have an old S available, or at least some measurements that you've seen in order to calculate the range, and then divide that by 4 to calculate sigma. So this is problematic, but this we'll do the best that we can under the circumstances and figure out a good approximation to sigma, and that'll help to get us kind of started on our way toward experimental design. Now, by the way, this formula that we mentioned here, that sigma is approximately the range over 4, I have observed this in course grades for many years, and it is a pretty reasonable approximation in the context of course grades. So I look at the range of grades between the smallest observed grade and the largest observed grade, and that range is typically quite reasonably, it's between 40 and 100, and that means that the range is 60 for course grades, and that puts the standard deviation at about 15, and that is pretty close to what I actually observe when I calculate standard deviations for course grades. So we see some practical application of this. It really is a good rough formula to help calculate, help estimate what the standard deviation would be. Okay, so that's the big problem in this experimental design, in this choosing the sample size section, is where does our sigma come from? And a problem, most problems that you'll see, it'll certainly give you some kind of hint about where to get sigma from. So there usually is some obvious way to pick a reasonable value for sigma. Okay, so that is how to choose the sample size. So let's go on with this particular problem we have been doing. We had the formula n was bigger than 1.96 squared over 4 squared times sigma squared, and now we need some kind of idea where about what sigma is. So best we can do in this particular problem, we had a prior study of a chemical process, and it produced a sample standard deviation of S is 21. So that's what we're going to use for our sigma. We're just going to say sigma is approximately 21. That's the best we can do. So we feed that into our expression, 4 squared times 21 squared. Now I pull out my calculator, which I have misplaced. Hang on a second. All right, you are going to get that n has to be greater than 105.8. So that is kind of what we call a lower bound for n. So that is the lowest value of n, which is going to give us the information that we need, which is an estimate, a confidence interval for the mean yield of this chemical process. Now, we may take n to be larger, much larger than that. There may be other reasons why we would want a different, larger n, but maybe it's inconvenient to do something like 100 and whatever, just 110 measurements is inconvenient for us, but we can do 120. If we're going to do 110, we can do 120. So we may go larger than 100 and whatever this is, 105.8, but we can't go smaller. We certainly can't go smaller than 105.8 and get the information that we want. And one other important thing to observe about this is that sample size is an integer. And we can't. We have to find an integer that's greater than 105.8. That means we always round up in these kinds of questions. So in this case, rounding would naturally round up, but sometimes. So that means in this particular case, I round up 105.8. So n has to be bigger than or equal to 106. Right, so 106 is our bare minimum for this project, and like I said, we could, under given other constraints, pick a larger value of n, but picking a smaller value of n won't work, and then picking a much larger value of n will be expensive. So, this gives us certainly a nice idea about the at least the kind of bare bones, the smallest experiment that we can do and still satisfy our curiosity here. All right, so we always round up. If I had come up with a number like this, n is greater than 105.2, I would still round up, always round up. So I would have to round up to 106 again in this case. Even though rounding, normally we round down, but in these questions I have to round up because I need an integer that is greater than whatever number I calculated. All right, so let's just now kind of review the situation. The idea is to find lower bound of n given a bound on the margin of error. So in the previous question, our upper bound on the margin of error was the margin of error had to be less than 4. And that gave us a lower bound on n has to be at least 106. So that's the question and the answer for these kinds of problems. Now, to express the process compactly, we're going to use some formulas, and so in order to use formulas, we're going to have to use a letter for this. This bound on the margin of error is usually represented by a number b. So here, b is equal to 4 in that previous question. So you have to identify when you're doing these kinds of problems, what is the bound on the margin of error, and then we're going to assign that bound to the letter b. And once we have that, we don't have to go through all the algebra every time. You can if you want, you're certainly welcome to, and it's not hard algebra, but that's not what this course is about. I don't want you to waste your time learning algebra. I want you just to get straight to the statistics. So in the formula sheets, I have put formulas that have been sort of pre-calculated. And so the formula, if our parameter is mu, if that's what we're trying to learn about, that's what we're doing inferential statistics on, if that's what we're trying to estimate, then the sample size formula is n is greater than or equal to z sub alpha over 2 squared times sigma squared over b squared. So you need values for z sub alpha over 2, and that comes from the confidence level, as always. You need values for sigma. This comes from previous estimate of s, or sorry, previous value of s, or estimate like the range divided by 4, and then b is the bound on the margin of error. And it will be specified in the problem. So all of these things should be specified in the problem statement. Sometimes you might have to ponder a little bit to figure them out. One thing that may be implicit is that implicitly confidence is 95% if it isn't given explicitly. So sometimes problems, even in this textbook, many times in real life, you will get a statistical problem and it won't say the confidence level that we're supposed to be doing the calculations at. And if it doesn't say, then you have to assume that that is 95%. So that is kind of the default confidence level if none is given. It's better to give it, and when you give your answers, I would like you to explicitly say the confidence level that you used when you calculated your answer. But sometimes the questions do not say that. You have to know enough to know that the appropriate value to use for confidence is always 95%. All right, so that is how we do experimental design when we are interested in measurement situations when the parameter in question is mu. We also have discussed in this chapter that if we have a discrete situation where the parameter that we are trying to estimate is p, the proportion of successes in a discrete survey or whatever, a Bernoulli, or sorry, not a binomial distribution. Then we have a different formula for n. That n in this case is z sub alpha over 2 squared, as usual. I also divide by b squared. But in the case of counting rather than measuring, we don't have a sigma, but we do use instead pq. And this is a little more problematic because, again, if I knew p, there wouldn't be any question. I wouldn't even bother with the statistics. I would just quote what p is. But I don't know what p is. And so, again, I have something that I don't know in this formula. It's very similar to, I didn't know sigma in the previous case. How did I what did I do to replace sigma? Well, I, just do the best that I can under the circumstances. Here again, I can just do the best that I can under the circumstances. I can use p hat, or sorry, p is approximately p hat from a previous experiment. That would be one way to do it. But the preferred way, I think, in this case, the method that is usually used is take worst case value of p. And that is p is equal to 0.5. And that means q is also 0.5 because p plus q has to be 1. So that is the worst case value of p, and that's what we should use in this formula for choosing the sample size in a discrete experiment. That's what I recommend, and this is standard practice. And we'll come back to this. We'll do an example in just a second. Okay, so last one that we have done in this course is when our parameter is mu1 minus mu2, the difference between two population means. The formula in that case turns out to be, and it's not obvious at all, this one's a hard one, so we'll just have to take the word of the mathematicians. So as usual, the formula has the z sub alpha over 2, I squared, the b, I squared, I divide those two numbers, but there's also another component to this, and that's that, we're going to use the two standard deviations from the two populations. So remember that there are two populations involved, and we're taking the difference between two population means. So this comes from section 8.5 in the textbook, if you want to review that. So in that case, we have two standard deviations, and we, as usual, need to approximate them both. So sigma 1 is approximately S1, and sigma 2 is approximately S2, and the S's are both from previous experiments. Okay. And there's one other thing about this that I should mention, and that's that when I apply this formula, I'm only getting a single value of n. But remember, there's two different values of n. There's n1 and there's n2. And so what I'm assuming when I do experimental design in this way is that I'm going to design my experiment where the sample sizes in both populations is the same. And that's not necessarily true. Once we go ahead and analyze the data, that doesn't necessarily remain true. So we may have started with the same number at the beginning, but there may be discrepancies. So people, if people are the experimental units, people do sometimes drop out of experiments, and that's one of our ethical obligations, is to allow people to withdraw at any time if they so desire. So we may find that these numbers differ. So when it comes time to analyzing the data, we still have to use the true numbers that resulted. But when we are designing the experiment, what we're going to do is make this assumption that n1 is equal to n2, and that is they're both equal to that value n that comes out of this formula. So that is an additional assumption that we have to make in the two population case, that the two, we're going to start with assuming that the two populations are the same size. and then the formula gives us that value n, which we're going to use for both populations. Now, if we're expecting that people may drop out, and I think when you do experiments that involve human beings, you've got to have that in the back of your mind as a possibility, then maybe that's one reason why you don't want this as your bare minimum, but you want to boost it up a little bit more. So when people drop out, you're still covered. So you might want to add a certain percentage onto that number, say add 10% more to code, so that you can cope with 10% of your experimental units dropping out of the study. Okay, so that is 8.8. Now I'm going to do one example. This is a nice example that you can see if you open the newspaper at any time. You'll see, so it's particularly during election time, you will see statements like the poll said blah blah blah. It is considered accurate to within 3%, 19 times out of 20. So that is quite typical language for a poll that you will read about in the newspaper. And I see this in particular in the Globe and Mail is very careful about stating its statistics properly. Other newspapers maybe not so much, but they should. And this is a nice way to state things that look that don't use too much jargon, that sort of your average reader might still be able to comprehend. We're going to analyze this a little more and try to see where these numbers come from, or what kind of implications they might have for conducting a poll. So this part here, 19 times out of 20, is our confidence. How confident we are in our results. And remember, our confidence can never be 100% confidence if we're doing samples, but we can be 95% confident. And that is exactly what that statement says. 19 times out of 20 means exactly the same thing as 95%. If you take your calculator, 19 divided by 20, you're going to find it equals 95%. So that is just a sort of friendlier way of saying 95% confidence, which is the way we prefer to say it, but newspapers like to be friendly when they write stuff. Okay, so that's one item here. We have 95% confidence. That implies that Z sub alpha over 2 is 1.96. So that we know something now about our study. The next thing we need in order to analyze this is our bound, our error bound. And there is our error bound right here, considered accurate to within 3%. So our error bound is, let me write 3% in a more proper mathematical way. So that is what our error bound is. Sorry, I shouldn't write it that way. I should write it this way. Our error bound is equal to 0.03. Right, and that means our margin of error is less than or equal to 0.03. So that's the second thing that we need. Now the third thing we need, remember we are in a discrete case, we're doing a poll. So that is discrete. So the correct formula is that n is greater than or equal to Z sub alpha over 2 squared divided by b squared times pq. That's our formula for the discrete case for a poll. We have Z we have B. What we're lacking is P and Q, but my suggestion to you earlier is that we estimate, or we max out P. Oops, not. We max out P at 0.5 and Q at 0.5, right? So that gives the maximum value for PQ. And that's just, a bit of high school mathematics, really. If I made P smaller, Q would be bigger, but the kind of trade-off would make the PQ even smaller, even though P is smaller, Q is bigger, but they don't balance each other out exactly. The graph looks like this. It's a parabola, if you recall from your high school math. And so if I take a lower value for P, it's going to lower PQ from its maximum. And if I take a higher value for P, it's going to still lower PQ from its maximum. So the maximum is reached at 0.5. All right, so that gives us all the four numbers that we need to actually calculate this thing. So n has to be greater than or equal to 1.96 squared times 0.5 times 0.5 divided by 0.03 squared. All right, so let's calculate that. I have to pull out my calculator here. All right, and a warning, sorry, I usually don't like to show students this. My calculator is something called reverse Polish notation. I don't have another one because I prefer reverse Polish notation. So I'm going to enter this in a very strange way. You can follow along in your own way using your own calculator. It's going to look different. Notice that my calculator doesn't have an equals symbol on it. And that's a clue there that this is something very strange is going on. So sorry, I'm showing you this. I normally try to hide it, but here we go. 1.96 times 1.96, there I squared 1.96 times 0.5 times 0.5. Now I'm going to take 0.03 and I'm going to square it. And I'm going to divide those two results. And there's my magic number. So let's go back to our so n being an integer has to be 1068. Remember, I'm rounding up. All right. So in order to make this claim that a poll is considered to be accurate within 3%, 19 times out of 20, the results of this section tell us that the poll has to have about 1,068 experimental units, or in other words, we have to poll 1,068 people. And so that is kind of this relationship here. This 3% number is connected to this 1,000 number. And it just thought that this is a reasonable way to conduct polls, that sure, we can be accurate to within 3% by surveying just over 1,000 people. That's become sort of the gold standard for polling. We have to survey somewhere over 1,000 people, so something like 1,100 people or whatever, some number greater than 1,068. And then we can make this claim that everybody wants to make, because we all want our polls to be accurate but not too expensive. This is a nice sort of conventional trade-off that we can make. Our poll is considered accurate to within 3%, 19 times out of 20, if we have at least 1,068 experimental units. So if you're a kind of a bare bones polling organization and you don't have a lot of money, You can lower this number, but then this is going to suffer. You're going to be less than 3% accurate. So most polling agencies kind of accept this. They think 1,000 people is a reasonable expense to pay in order to get that 3% accuracy. And if you wanted more accuracy, you would have to use this formula to increase, it would increase the value of n. If you want more accuracy, that would make this number smaller, which makes the whole fraction bigger, which would make n bigger. So you see more accuracy is going to cost us in terms of a higher sample size. All right, so that's an example of how this kind of formula, this experimental design strategy is actually used in practice in polling that you'll see all over the place if you open up a newspaper during an election, for example. All right, so that's it for 8.8 and for Chapter 8. So please do the problem set. For Chapter 8. There will be a quiz. Will open on Thursday. That means you can do it at your convenience. Anytime up to 1 week from Thursday. So if you're ready on Thursday, you can go ahead and do the quiz on Thursday. If you feel you need the weekend to study, you're welcome to do it on Monday, Tuesday, or Wednesday of next week. Once you start the quiz, you will have 1 hour to complete the quiz. So don't start it until you're ready. Because then you're committed. You have to finish it within 1 hour. The quiz will be multiple choice. You will still have to solve problems that are like the problems in the problem set, but the answer will be a single number, and I will give you a multiple choice. It will be graded automatically by the UR Courses system, and so you'll be able to see your grade right away for the quiz. All right, so I've implemented these changes to our quizzes in order to accommodate the shift to online. In particular, I want to give you some time to prepare. Certainly this first time, I know everything's going to be disorienting for us. So please make sure you are well prepared before you start the quiz. And I think that'll be to your benefit. It'll give you, you won't have to come in on Thursday and write the quiz. You'll be able to write it at your own convenience as you become prepared. Anyway, all the best. I will be online on Thursday where we can discuss this some more. So if you have any questions, please send them to me anytime or connect with me online. I'll be available for chat or email on Thursday during our regular class time. All right, all the best. I will be back soon with Chapter 9.